Hello, my name is Inês, and I'll be telling you about efforts on identifying behavioral signatures of individual learning variability, which is work developed at the International Brain Lab, which I've done together with Fanny Cazette, Eric David, and Zach Maynan. So we've leveraged the IBL large behavioral datasets of mice who were trained to perform a simple visual discrimination task. In this task, they were rewarded for correctly reporting the location of a visual stimulus presented on a screen by moving a small steering wheel. Importantly, we observed that after mice learned the task and performed at proficient levels, there were no significant differences in their behavior across the different labs of the collaboration, as is seen here in the superimposed average psychometric curves of each lab. However, despite our highly standardized and automated training protocol, we see that mice's learning profiles vary a lot, as is seen in this plot, where I show the learning curves of each mouse, with the gray lines depicting the performance across training sessions, and the black dots denoting the moment in which each mouse got trained, classified as trained. So this observation of the great variability in learning speeds brings us to the motivation of this work. So we here hypothesize that the variability in learning speeds reflects variability in learning strategies used across mice. In order to test this, we worked on carefully characterizing individual learning trajectories, and we ultimately expect that the observed learning differences can be clustered into discrete strategy modes, which might explain the observed differences in learning speed. So to start with, we looked at the distribution of learning times here on the right, which was basically obtained from the time it took for each mouse to reach the learning criterion here in the black dots. We see that most mice learned the task in relatively short amounts of time, but some mice took much longer. So for the purpose of relating specific learning features to learning speed, we discretized learning time into 4 quartiles, pink corresponding to the fast learners and light blue to the slower learners. And we'll keep this color code throughout the presentation. What we then did was to characterize individual learning trajectories, but because these had different lengths across individuals, like for example, a mouse from the first quartile in pink learned the task in much less sessions than a mouse from the 4th quartile in light blue. And so we normalized learning trajectories into the same number of bins. So by either compressing or stretching the original learning curves into a fixed length, we could now superimpose learning curves of different mice. So now the x-axis represents fraction of training time instead of time. And this allows us to identify differences in the learning trajectories beyond learning speed. So for each bin of the learning curve, we characterized behavior based on average estimates of accuracy, reaction time, movement time, number of movements per response, win stay and lose shift strategy probabilities, and response times conditioned on these trial types. And we'll look into some of these in more detail later on. So based on this behavioral characterization, we then investigated whether individual learning trajectories segregate in a lower dimensional space according to learning speed. So for that, principal component analysis was performed on the behavioral features of each training bin. And here I'll show you the results obtained for the first 2 principal components, which together accounted for more than 50% of the variability in the data. So here on the right, I represent the learning trajectories averaged per quartile using the same color code as before, where the upward-facing triangles denote the start of the training and the downward-facing triangles denote the end of the training. So interestingly, PC1, principal component 1, seems to have captured the evolution of behavior along training time from right to left. But more interestingly, even PC2 seems to segregate learning trajectories for different learning types, namely the faster learners with higher values for PC2 and the slower learners with lower values. So then to further look into what PC2 actually captured, we are showing you here the behavior features with the biggest weights on PC2, which correspond to the probabilities of using a loose shift strategy, a win state strategy, or a stimulus bound strategy. So, but then what is actually going on regarding these strategies in learning? So overall, when we look at these throughout learning, we see that as expected, mice increasingly adopt a stimulus bound strategy, which is from early to late training, which is the optimal strategy in our task. But we also see, interestingly, that early training is characterized by an increased use of win state strategy, um, and a decreased use of loose shift strategy, overall meaning that mice tend to repeat this choice of the previous trial more than predicted by chance, and independently of reward feedback. But we also see that this tendency vanishes throughout learning, as is expected, as this is not an advantageous strategy. So then when we look at these same metrics split per quartiles, although noisy, we see that the faster learners have a higher use of stimulus-bound strategy in the second half of the training period. And we also see that the faster learners seem to have a smaller tendency to repeat the action of the previous trial, as shown by a reduced use of win-stay strategy and increased use of loose shifts. So overall, these results suggest that differences in the amount of stimulus-based and history-based strategies might underlie differences in learning speed. And current efforts include further characterizing learning trajectories based on video and wheel movement data, which we believe together with our current results will help us more completely define what might be discrete strategy modes, which might explain differences in learning speed. And with that, I finish and thank you all.